Very good morning and welcome to the fourth day of the GIAN program. Actually, if you look at the schedule, we were expected to have Professor Karmalkar start with the Himalayan ophiolites. Unfortunately, he is unable to join us today. He will join us tomorrow. So, I will continue the next lecture that was supposed to happen in sequence with his. So, I will be talking about a little bit about UHP metamorphic terranes in the Himalayas, and we know that in the Indian Himalayas we have one very well established UHP terrain. So, first of all, this work is of course ongoing with the JET, and that is why I put the logo there, but yeah, it is something that we started way back in 2008. When we went to field for the first time and looked at these eclogites, which were ultra high pressure, and then subsequently work has evolved. So, I will be giving primarily a petrological perspective and not a geodynamic model, okay, because that is not something what we do, we work on the petrology. So, I will give you that. We all know that we have seen this cartoon from Oliver's slides, and we know that the continental crust subducts to mantle depths, and that record is primarily preserved in rocks which sometimes undergo high pressure and very rarely ultra high pressure metamorphism. Okay? So, when you have the continental crust that subducts, you primarily have what we call as there has to be something that is actually dragging this continental crust down, and that is typically your oceanic crust or something denser. Okay? So, in the Himalayas and in many ultra high pressure, in many orogenic belts, you see that the denser crust, okay, which is primarily oceanic in composition, or it could be gabbroic or basaltic, typically gabbroic. That subducts to great depths and then it comes back sometimes, it bounces back sometimes. Okay? So, the geodynamic record of subduction and subsequent exhumation can be studied now by looking at orogenic belts which possess ultra high pressure to ultra high pressure metamorphic rocks, and these rocks are typically represented by your blue schist facies rocks and your eclogites. Okay? And they are able to tell us what is the history of this subducting slab. Okay? Not everywhere in orogenic processes, not all orogenic belts have ultra high pressure or high pressure, mostly high pressure, but not all the time ultra high pressure rocks preserved, and that is why when we find them, it's very important to understand both prograde or subduction processes as well as exhumation processes. Okay? How do you understand whether a rock has undergone ultra high pressure metamorphism? It is primarily by the presence of index minerals like coesite, and which is the high pressure polymorph of silica, and when you have that present either in its pure form or as a relict, or when it is as a pseudomorph. Sometimes most of the times you do not find pure coesite, you find the pseudomorph, or you find the alpha quads. Okay? So, when you find that, we know that the crust has reached UHP levels, okay, ultra high pressure levels, and that can be summarized or looked at in this graph or in this PTD diagram, which primarily tells you that when the crust is subducting, it has to reach this depth somewhere about 100 kilometers at least for it to undergo ultra high pressure metamorphism, and anything below that is typically high pressure metamorphism. Okay? So, metamorphism of crustal rocks, both the continent part and the oceanic part, when they subduct to depths greater than 100 kilometers and they are able to crystallize coesite as the index mineral, then you know that we have reached UHP levels. Okay? So, this is typically what we use to understand the subduction and the exhumation history of our rocks. Okay? If you look at the global occurrences of course, I think it was in 1953 that coesite was first found in natural rocks. Okay, so it was experimentally tried before that, and of course subsequently, but Coes was the first one who identified coesite. I think that was in the Western Alps in Dora Maira. I'm not extremely sure where he found the first. Chopin, okay, Chopin was, but yeah, so Coes identified that silica has a high pressure polymorph, which is coesite, and Chopin was the first guy who identified it in the Dora Maira. So the Dora Maira then got established as an ultra high pressure metamorphic complex, and subsequently you have several more. So you have the Western Gneiss region in Norway, which is here. You also have the Dabi Sulu in China, which is somewhere here, this is here, and of course you have some in the Alps. So you have also in the French central, in the Massif Central. You also have some in the Greenland province, okay, and China has now several localities in China have now people have identified the coesite and now have started to move from a high pressure to an ultra high pressure complex, okay. India or the Indian subcontinent is unique because we have the subduction there, we have the suture zone, but it was very recently, it was only in 2001 that the coesite was identified in two locations, one in Kaghan in Pakistan, and then subsequently pretty much the same year or the following year in Somorari. So it's these two locations which sit very close to each other and very close to the collisional boundary or the belt, you know, the, what is that called, the, yeah, so it's close to this point here. Syntax, yes, where you actually find both the localities, okay. So of course, after this a lot of research has actually happened on ultra high pressure metamorphism. People have started to look at that more seriously and not just say that yes, coesite is found in meteorites or in extraterrestrial material, but we also find it on the earth and primarily in continental settings, okay. So some very classic or common structural and lithological characteristics were observed between these different terranes, okay, and primarily all of them were lying between major continent-continent collisional belts. So we didn't have, so yeah, it was when two continents collided, there was a possibility of finding UHP rocks, and these are of course photographs from the Somorari because I don't have photographs from other locations, but it's, if you look at literature, especially the paper by Liu et al. In 2001, it shows that, or he says that most of these terranes which are now UHP, recognized UHP terranes, they all have several similarities and they primarily have pods or lenses of mafic material which have undergone, which have basically been subducted to depths and now do show UHP signatures. So they occur as pods or slabs within typically what we call as gneisses, okay, quartzo-feldspathic gneissic units, and these pods, they preserve the UHP signatures, okay. Of course, most of these, because we are in the continent-continent collisional belts, they have continental affinity. So the chemistry, the geochemistry also shows that we are in a continental setting. But then the question comes as to why do we have this pod which is mafic, and where is the mafic material coming from? So of course we are looking at an older protolith which has then got subducted with the continental crust and then exhumed back, and the exhumation is primarily because of the buoyancy of the lighter material, the felsic material, which is bringing it all back up, okay. So these actually lie at structurally higher levels in most units. So we look at Somorari as an example and understand that. The exhumed crust now lies as a thin sub-horizontal slab in the upper continental crust, and it is bounded by normal faults. Okay, so if you look at the structural aspects of many of these terranes, you have similarities. So they are bounded by normal faults at the top and reverse faults at the bottom, and probably that aids to in the exhumation process. I haven't really worked on structural aspects of these, especially of Somorari, but it's there in literature. Okay. What we also find is that we do not have any island arc, volcanic or plutonic equivalents associated with these terranes. So there is no subsequent magmatism that was happening. It was just an exhumation process. And yes, we do find late stage granitic plutons which are associated very close to them, to these terranes, and in Somorari we have the Ladakh batholith which is very close. So if you look at Somorari and you look at all the parameters that have been laid out, it fits the bill of at least from field observation, it definitely fits the bill of being very, very similar to other UHP terranes which you find world over. Of course, we need to confirm all of this by petrography, geochemistry and other aids. Okay, so we did that. We sampled these rocks way back in 2008, and we've been subsequently sampling them whenever we go to field, and every time we go we look at something different, and we are trying to kind of unravel the story a little bit better. Okay, so if you look at the Himalayan belt, you have, like I said, Kaghan, which is the where is Kaghan? This is Kaghan, and I've marked it in the wrong color. I'm sorry. So no, sorry. The blue ones are UHP. So you have Kaghan, which is UHP, and Somorari, and everything else should actually be in red. So yes, we do have places where you do get high pressure rocks. So primarily blue schist facies and eclogite facies sometimes, but the coesite has not been identified. So we do not put them under UHP category. Okay. Coming to Somorari, we have looked at this map earlier. Okay. So if you see, Somorari is a very small 100 kilometer by 50 kilometer square kilometers body. It's a crystalline, it's a crystalline complex which sits right below the suture zone. So this purple band is the suture zone, and you have the ophiolites, the Nidar ophiolites, which are sitting on top. Okay, what is very interesting about Somorari is that it's now established that it was primarily the leading edge of the Indian continental plate, which got subducted and then got exhumed back. Of course, the models, there are several models which have been proposed by Dissegoy, by Julia and other people like Stefan Gouliet, but I'm not going to go into the details of that here. If you look at this geological map, of course these are sampling locations. Most of the eclogites that you find in the Somorari, they are all retrograded except for two we found which were pure eclogites, and they preserved all their minerals intact and they didn't actually show retrograde features. But everything else is actually a retrograde, it's retrograded to amphibolite facies. So we are typically looking at processes during exhumation more than what we see during prograde. So that is typically what happens with metamorphism, because it kind of obliterates at times all the prograde signatures and you are left with retrograde signatures. Okay. If you look at the map, it's a dome shaped or an oval shaped structure. This is primarily, the yellow is the quartzofelspathic gneisses. So it's extensive and they are highly deformed at places and grading to, in fact, at some places to myelonites also. But since that was never really the focus of our attention, and maybe now we'll switch and look at the crustal rocks also, or the felsic rocks also, we kind of never really worked on those. Okay, but some people, very few people have worked on those in literature. If you look in the literature, you will find information about the quartzofelspathic gneisses also. But the eclogites have been intensely worked now because they preserve the coesite, they tell us different things about subduction, histories, etc. of the, at least of the Indian tectonic, of the Indian plate. So yes, if you look at these field photographs similar to the earlier field photographs, let me go back. In fact, that one is a better slide, a better photographs because they are recent ones. Yeah, they occur as pods. Okay, so this is the primary eclogite, which is pure. It does not show retrograde signatures. Okay, and all of these lenses, which are actually at higher structure, at a higher level. So they are quite, this is like maybe 100 meter, more than 100 meters height, okay? And we are already at 5,400 meters elevation above sea level, so it's quite high. So all of these pods or these lenses, in fact, these slightly black lenses, there are several of them. There are more than, I think, 100 there, okay? They are all retrograded, okay, and they show retrograde features in terms of their minerals, and we'll look at that a little later. So they actually have a very sharp contact with the host rock, and it's not a gradational contact. Even this one here, there are some faults on both sides, but yeah, this is how the eclogites look in the gneisses. Okay, so field wise, other than the quartz of feldspathic gneisses, which probably have more structural elements preserved in them, the eclogites just look like boudins or lenses, or that's all. They don't really show any signatures. Of course, the core of these lenses are more coarse grained. As you go towards the edges, they are more fine grained, and those kind of features are definitely observed. Okay, coming to the established PT path. This has already been published in literature actually. So there are several people before me. I have not put the references here, unfortunately, I am sorry for that. But these PT paths were kind of worked on by several workers before me. What I tried to do was, I tried to put this into the perspective of petrology, okay? And I'll show you that first. So if you look at this PT path, we know that the eclogite started, or the protolith which got metamorphosed to form eclogite started at, of course, crustal levels, and then got subducted to depths up to 120 kilometers, and then it came back up, okay? But how do we understand that? We understand that, at least we have done it through the petrography or the petrology, and you look at these rocks, they are beautiful core, and they have other minerals like omphacite, which is the soda rich pyroxene. You have phengite, which is the high silica mica, amphiboles, which are typically sodic in composition. So you have baryosite, and some places, not here of course, but you have, yeah, typically baryosite, and then quartz and coesite, which has been identified. So all the previous workers who kind of worked on these rocks, I think Sachan was the first one. Sachan Mukherjee from Wade Institute was the first one to identify coesite, and he tested it with the help of the Raman. Subsequently, no other worker has actually found the coesite in the slides. Okay, I think it's a chance preservation. Fortunately, we've been able to do that. We got them in our slides, and we got several of them, several grains. So we got 8 grains, which actually are coesites. So of course, I'll show you that later. We have a lot of secondary mineralization or secondary minerals like the zoisite, the epidote group mineral. We have the feldspar. Of course, we have the pyroxite, we have the chlorite, and then we realize that these are actually retrograde products. They're not the primary peak UHP products. Okay, so typically garnet, omphacite, okay, phengite, amphibole, and at places quartz and coesite. Okay, this is how they look. They are beautiful euhedral idioblastic grains with cores full of inclusions, rims which are relatively free of inclusions, and of course at places completely devoid of any inclusions. Okay, these are the grains which are the coesites. You can see they are characterized by the typical radial cracks, and those are nothing but expansion cracks because of during exhumation. So they are expansion cracks, volume, the volume increases, so it cracks the host mineral. Okay, these are of course garnets which have got retrograded to chlorite along cracks, and they are more rounded, and they are not as idioblastic as the UHP signatures. Okay. Based on all these minerals which occur within the garnet cores, we were actually quite confused as to why we are getting amphibole, sometimes even mica, and other things within the cores, and what do they represent. So we realized that it's at this point we have already reached UHP stage, and there is no way to understand what the protolith was, or where did these rocks start from, what was the starting point. And later on, when we actually analyzed them with the chemistry, we realized that all these inclusions which are present even in the backscattered images, you can see it very clearly. The light is too much, I'm sorry, but yeah. All these inclusions typically represent the pre-UHP phase. So they represent the protolith, parts of the protolith which are actually preserved. So all these minerals like the amphibole, the sodic amphibole, the epidote, the clinozoisite, all of them which are present in this are typically represent the pre-UHP stage. And another thing that we caught was the zoning. The garnets are intensely zoned. So at lower pressures or lower temperatures, they are most calcium rich, and as subduction increases, they become more Mg rich. So that was, so this association was established, and yes, confirmed with previous reports that all these minerals which are present within the garnets are actually a pre-UHP assemblage, and then you move as subduction or metamorphism increases, prograde metamorphism increases, you get signatures of garnets which are more Mg rich in the rims, you get the presence of omphacite, and you get the presence of coesite. Okay? So yes, the second phase or the second association would typically be a more calcium rich garnet in the core and a magnesium rich garnet in the rim with the presence of omphacite and coesite. Okay, and of course rutile and fengite, they are all accessories. Like I said, we were able to identify the coesite within our samples. We found several grains, so these are 6 or 5, no, this is the 6th one, yeah, so 6 grains of coesite, which we then of course confirmed petrographically, because there are again in literature different ways to actually confirm whether you're actually looking at a coesite, and of course we confirmed through Raman studies. Okay. If you look at the coesites, they are typically always elongated, small grains, and they have what we call as an isotropic halo around them. If you look at them, they are typically surrounded by these very intense radial cracks. Okay, that's a characteristic feature. Even when the coesite completely transforms to alpha quartz, you should get radial cracks, and that is a, what do you say, diagnostic indicator of whether coesite was present or not. The radial cracks help you to understand that. What do you also see in this image is very, very clear. You see a nice rim and you see a core, and this rim is nothing but the coesite changing to alpha quartz during exhumation. Okay, so they will typically have different textures under the microscope. Okay, so this rim is called as a palisade quartz texture, and it is very, very well preserved in these samples. Okay, not every place on the earth actually has this. So we were lucky enough to actually get this, and we've been able to do more detailed Raman mapping to understand whether this actually works. Okay, so all these grains in fact have both the phases in varying proportions. So coesite, quartz, and they are, so what we could capture was typically how the transformation goes. So you, at places like here, you get complete transformation. So the amount of coesite which is left in the grain is very less. This is of course in natural samples. We could only understand how this works by looking at experimental data. Okay, so experimentally, at what depth, especially at what temperature and what pressure complete transformation takes place has been done by workers like Perilat. He was the one who actually gave us the detailed transformation of coesite to quartz, and we use that to understand this information better. Okay, so I'll come to that. I'll come to what temperatures, you know, these transformations work with, or what happens a little later. Atoll garnets, another very fascinating observation that we found in these samples. So you have whole porphyroblastic garnets, okay, which are full of inclusions, and you also have garnets which have a central part which are completely occupied by another mineral. So here it's fengite. It's the mica which is occupying the central portion, or I would say so this is the central core, and then you have a mantle region which is now occupied by phengite. And this was peculiar because not a lot of information at that time, at least when I started the work, I realized that I don't know why this is happening, whether it's a UHP stage formation or it's post UHP, no idea. But when you looked at backscattered, they also showed zoning. So they are zoned, they have Mn rich rims, and you also have some part of the core which is calcium rich. So they're following compositionally the same signatures as the whole garnets, but there's something else that's happening here which was kind of difficult to understand at that point, but yes, we've been able to figure that out now. So if you look at the atoll garnets, they are typically a nice euhedral shaped garnet with a central well preserved core, and you have between the core and the rim you have an association of different minerals. Okay, this is also actually associated with symplectites of calcium rich amphiboles, plagioclase after garnet. So we realize that by looking at the texture of the other minerals, we are probably looking at a post UHP phase, and these are not UHP. So this is something related to exhumation. Okay, so here the calcium, so the garnet is again Mg rich at the rims. I have not put that map here, it's here. The Mg rich at the rims, and you also get calcium rich amphiboles, plagioclases, biotites, etc. Like I said, all these garnets are zoned, and the zoning ranges from a calcium rich core to a magnesium rich rim. Okay, so calcium Mn rich core with a Mg rich rim. And of course we then used coexisting mineral phases like phengite and garnet, phengite and CPX, garnet and CPX to then calculate temperatures. You know, at what temperatures were these minerals equilibrating and remaining stable. So we did that for both the whole garnets. The core, like I said, was full of inclusion, so we used the phengite and the CPX in the core of the garnet to come up with temperatures, and we used different thermometers. The one that really fit the best was the garnet phengite, because they seem to be in perfect equilibrium. So we get a temperature of 635 degrees. Of course, I have not worked out the pressure here because you need other minerals which are stable to calculate pressure. So pressure was calculated based on garnet, CPX and phengite at 2.8 GPa. The rims of course showed higher temperatures, which was of course because you're subducting, the crust is subducting. So you're getting higher temperatures at the rims, which is nearly 800 degrees Celsius, and you're getting there was no pressure that was calculated here, so we didn't use a barometer here. When you looked at the atoll garnets, we realized that the pressure is in fact, the temperature is in fact dropping. So out of these two traverses, I don't remember which traverse we use now for these calculations, but the range of the temperature is now 614 to 675, so definitely lower than UHP. So the rim of the garnet represents the UHP temperature of nearly 800 degrees. Okay, and the atoll garnet represents a lower temperature, or it's at a lower temperature at a lower pressure. So then that gave us an idea that maybe this is, like I said, post UHP. Yes, we get different other minerals which are primarily post UHP. You get garnets which are intensely fractured and now filled up with chlorite. You also get a biotite, which is a low temperature mineral now. You get hornblende. Okay, you get a lot of symplectites of plagioclase and CPX symplectites of plagioclase after CPX, and of course you get the calcium rich amphibole, which was not present earlier, and also this is in fact the sodic amphibole which is present. So if you look at the amount of retrogression that the rock has undergone, these are some possible reactions that could have taken place to give rise to the amphibole and the plagioclase. So the omphacite would typically break down, the omphacite in the presence of quartz and water would break down to form the amphibole. So that's how the transformation, we believe that happened. If you look at comparing the data that we generated on the whole garnets and the atoll garnets and compared that with the experimental work by Perilat, we realized that there was a very good match. Okay? Based on these images, the Raman mapping images, what we did was we used a software, an open source software, an image processing software to calculate in this area how much coesite could ideally be present and how much quartz could be present. And with those numbers, we then looked at what experimental data says. And it says here, I can't read very well from this, but it says that the quartz to coesite transformation, which is the complete transformation of 100%, happens at a temperature close to 800. Okay? So this is 800 and the pressure which is given is 2.8. So of course the pressure doesn't match very well, but the temperature definitely matches. Okay, so that was one. But see, nowhere in our slides or in our samples we get complete transformation. There's always a little coesite left. So you have to take these values with a little pinch of salt. But it matched well with what we found for our garnets. Sorry, I'm going back. So it matched well. So when you say 800 as peak transformation, because quartz would transfer to coesite at 800 and we are getting a value of say 768. So that kind of matched well. And again, the retrograde transformation of coesite to quartz happened at 2.3 pressure GPa and the temperature was somewhere around 700. So that also matched with our values of 675 and 2.3 GPa. So that gave us a fair understanding that maybe we are on the right track, especially with these temperatures. But of course, there was no way to confirm it other than this. We had to use this data to make sense of what we were seeing in the coesite and the quartz transformation. So yeah, near complete transformation of alpha quartz to coesite probably happens between temperatures of 700 to 800 degrees at 2.8 pressures, GPa pressures. And coesite undergoes partial transformation to alpha quartz during exhumation between 600 to 700 degrees Celsius. And that is confirmed by both textural studies and Raman mapping. And of course, we have confirmed it also through experimental work now. Okay? Yes, if you look at this PT path which I showed in the beginning, we try to fit all the petrological work or all the petrological data that we generated in this PT path and these are our garnets. Okay? So you actually start with nucleation during at the onset of subduction, somewhere at 1.1 GPa, 500 degrees Celsius, and approximately at a time of say 57 million years. So that's when the Indian plate just started to subduct beneath the Eurasian plate. Okay? Followed by garnets which are formed. Okay? These are typically garnets with euhedral boundaries, idioblastic, and they have inclusions of amphibole, clinozoisite, etc., and that represents a part of the protolith which has got subducted, and now you're at 30 kilometers depth. So you're still within the blue schist facies, you haven't really crossed into at least high pressure, ultra high pressure. Followed by the formation of the coesite with the omphacite. This is typically at higher temperatures, 760 or nearly 800 degrees Celsius, 2.6 GPa, somewhere at 53 million years. This is typically what you would find for this association of rock, of minerals in the eclogite now, in the pure eclogite. And now we have actually crossed the coesite quartz boundary. So we typically have the formation of coesite. Okay? Of course, these garnets or these rocks have now started to exhume back, but we still don't see that in terms of the petrology. We still get higher temperatures of say 780 degrees. This has actually not been recorded in any of my thin sections. I haven't got this number, but Preeti Singh from Delhi, University of Delhi, she has worked on these and she has got this association. So I have still put it there. So 2.8, so I should put the reference there. In fact, I should update this. But what we realize is that most of the minerals which have OH in their structural setup, they start to break down, okay, because of the onset of exhumation, and you have a lot of fluid inclusions. This is my thin section, so you have a lot of fluid inclusions and especially phengite, which probably start to break down and give rise to the formation of fluids, and then you start having what we know as fluid infiltration within the garnets to then go on to form atolls. Okay, so this is primarily at a lower temperature on the way back, okay, as these rocks are getting exhumed. So at 768, nearly around 50 million years, I've put a question mark here because this has not been worked on. I mean, we don't have this actual age, but it's pretty much between 53 and 47, okay. So typically you start getting the formation of atolls because the fluid starts to infiltrate and it along these cracks in the garnet, and it modifies the interior of the garnet and it starts to replace them with lower temperature minerals, okay. Again, yes, so the atoll, this temperature has been calculated 734 to 614 at 2.3 GPa and 47 million years is typically where most of the atoll formation kind of was complete, and you're able to now see beautiful atolls in the form of these pictures, okay. You also get a lot of symplectites, okay, which is again a retrograde feature, and formation of chlorite, okay, biotite, etc. And of course, these symplectite formations, which is represented here in the form of D, they are of course at a lower temperature of 400 degrees Celsius, nearly 1 GPa, and when the crust is quite shallow now at 29 million years. So this is a sort of petrological perspective on what happened with these eclogites. We also have a geochemical perspective which I haven't shown here, but a lot of movement of all your large iron lithophile elements, because they are fluid mobile, so they actually have kind of been elevated. We've done those mass balance equations and also worked out that yes, these eclogites definitely have undergone some metasomatism, okay, on their way back. I haven't shown that here because I just wanted to give you an ultra high pressure story, and I think I've stopped very early. But yes, this is how the Somorari Lake looks like, and this is a part of my field area, the Puga Nices. But yeah, I'm open to questions, so we can have a lot of questions. So if you have anything you want to ask or you want to say. Yes, yes.
So about the cracks around the
yeah.
site. So you mentioned with the hypothesis that it's during the exudation that there is a
volume increase.
Yeah. Could it be that it has to do with the coesite itself, phase change?
Yes, because coesite is denser, so it's more compact, and quartz is not as compact, so it expands. And usually the garnet also shows the cracks, and even the zircon, if it's present in zircon, because for coesite to be preserved, you need a competent host mineral. And the only two host minerals that have been found to be very competent to host the coesite is the garnet or the zircon. And typically it's the garnets in continental rocks, especially in metamorphic rocks like this, but the zircons also are known to host the coesites. And they are what we call as there's something called as a pressure vessel effect, because they are the host is also putting the pressure on the coesite to remain intact. So it's
It feeds the debate about what is measured terms of pressure? Is it the differential stress, or is it really the weight of the rock column?
I think it's both.
It might be both.
It's both.
So there might be a way to do some mechanical investigation modeling around the quartzite and the garnet, looking at their differential strength,
Right.
density.
Yeah, I'm sure there must be a way to do that, but someone has to attempt this. I think that can be done more experimentally, not really on natural samples.
And this picture,
Yeah.
so yeah, I think that's very, very compelling. And you could use that. As you were presenting it, I was thinking, okay, we should use that as a probe for temperature or pressure changes.
Yes.
This transformation using the relative proportions. I would say that if you want to do it very more precisely,
Yeah.
you should do it in 3D. Because you never know where the cut is.
Yes.
If it's on the edge of the rim or it's in the middle.
Absolutely. But the problem is, like I said, these coesites are preserved on one thin section with a cover slip, and my biggest.
That's very good. No, that's very good. And
Yeah.
do what you can with what you have.
Yeah.
Maybe one thing that we can do now is to look at where these 6 samples come from. Are they from the same rock or are they from different structural levels?
Same rock.
Same rock.
They're from the same rock, from the same sample, and unfortunately, yeah, it's from the core, the rim of that body. So it's not from the core. Yeah, it's from the rim. So.
You could do this type of, if you're lucky enough, you can do a translate across that eclogite body and go from core to rim, and then also look, so that would be one way to look at the relationship between these reactions and the textural position within the
Okay. But you know, very frankly, we have not really sampled all the lenses. It's just impossible because some of them are very at great heights. But if we attempted,
looking at samples from different structural levels.
we should do that. Someone has to volunteer to climb and break the samples. Yeah.
Other than eclogite, in which rock samples did you encounter cohesion? Not in much greater amount, but at least just the encounter.
So I think in literature, it's only the eclogite that actually hosts the coesite. You could also get the coesite, yeah, so it's either coesite or diamonds, microdiamonds, but they are all in the eclogite. There is no other rock which will have the coesite. Yeah. Yes, Deepak.
How does phengite influence the pressure temperature part?
So phengite is primarily a high silica mica. So when you have, so biotite is at a lower level, and as the crust subducts, the mica will change to phengite. So the silica content is, I think, about 3.5 SI cations. So that helps to, in fact, tell us about, so the equilibrium with, that's why we use that as a thermometer with the garnet, because it's high silica. Yes, somebody had.
You said something about symplectite. What is that?
So symplectites are nothing but two mineral phases which kind of coexist together. I don't know where the picture is, but they are typically a result of breakdown of the original mineral. So the omphacite here, or the pyroxene, is breaking down to form plagioclase, feldspar, and that's through a reaction. So they basically have a symplectic association. So they occur together. You are able to see both the phases, mineral phases.
And in terms of major elements, chemistry, these eclogites, where do they stand in terms of silica content?
So they are typically basaltic. They have a basaltic profile. So like I said, the protoliths are Permian basalts. That's geochemically we have proved that, but I think they definitely represent an older phase. I don't think they're Permian. We still need to figure out. But yeah, they're basalts. So they have silica contents ranging from 48 to 50%, 52, I think.
And you say that, so you mentioned phengite.
Yeah.
As maybe part of it is the primary phase.
Sorry.
The phengite.
Yeah, it is the part. It is the primary phase.
It's a weathered basalt or something that
We don't know. We don't have I can see only the eclogite now, I don't know. And in fact, where these basalts or, you know, they are exposed quite south in the Kashmir side, not in the Ladakh side. So if you say that they are the protoliths, but they've been proved, and we've got signatures, geochemical signatures which say that.
What I'm getting at is the fluid story.
The fluid story, yeah.
So it looks, you need it. The idea, the basic idea is that the amphibolites fishes to eclogite fishes tradition is related to fluid.
Yes.
So you identify part of this oily fluids in the OH of the finite,
Yeah.
primary finite. But then it is here's different from that basic model is that then you got fluid influx back into the eclogite.
Yes. So that's probably because of the.
It's also then sucking back fluids into the eclogite again.
Yes.
On the way back.
Yeah, we've been actually able to prove or understand what happens on the way back and not really what happens on the way down very well. But there are some studies which have said that on the way back up, you have a lot of fluids which were released. That's been proved experimentally also by a group in Germany. But all these fluid inclusions are probably evidence that in the retrograded eclogites that there was fluids which were present.
You got your amphibole already in the current course, right?
This, yes, could also be a reason for the fluid while going down, yeah.
Also, what are the dating techniques which are used?
So here we didn't use like in situ dating as such, we used thermometers. So we used two minerals which were in perfect equilibrium with each other, and we looked at we probed them, we got their mineral chemistry, and then we worked out the temperatures.
So, ma'am, by any chance, are there any literature showing the fluid inclusion study as such in particular?
So yeah, when we actually got the things, yeah, there are studies. I think only two. There's one by Chatterjee et al., which basically tells you about what kind of fluids were present in the Somorari eclogites. But we didn't attempt that because you need very intense equipment and heating stage and stuff like that. And that was never the primary focus of the work. So we were looking at it more from a petrological perspective. So yes, fluids, because someone has already established them, we didn't kind of go ahead and then recharacterize what fluid inclusions were, what was the composition, whether they had a fluid phase or a solid phase or a gaseous phase. We didn't do that. But maybe if there's someone who's interested, we can retry. Yes, so I think I'll stop because, and if you want, we can take the break now, or we can, has the tea arrived? If it is arrived, then we'll stop. So yeah, thank you for listening, and I hope to work more on these rocks, at least on the eclogites, for something else maybe, and try and, yeah, please.
So the core sites you found these two locations are
So yeah, so basically, yeah. So out of the entire sample set, we sampled about 25-30 eclogites, but when we were actually sifting through them, you know, we ended up throwing out most of them because they were amphibolites, okay, and we didn't want to work with the amphibolites, but we realized that we shouldn't have done that actually, because we could have got a better story of the exhumation path. But what we did was, we found two samples which were pure eclogites, okay, and so one of them has the coesite, and one is purely with no coesite, yeah. But
they kind of concentrate only in the northern parts. Down also you showed some.
Very frankly, they are all in this lens. It's in this big lens and this part, and at this structural level where you find them, we couldn't really climb up here because it looks quite accessible, but it's not.
As in geographically, right now it's towards the north, and then as we move towards the east, you said
Are you talking about this?
You mark something in blue and red in your location map. The previous.
Okay, this one. Okay, so
the blues actually give you the.
so yeah, this one is actually Somorari. Okay, so I color coded them wrongly, very frankly, and I did this yesterday night, so I apologize for that.
The reds are what again?
The reds are in fact supposed to be the UHP, but they are now just high pressure. Okay, so this is Somorari, and this is Kaghan. So these two locations have the coesite. and everything else is all just high pressure. Blue schist.
The that white exists only there then. No?
Because I told you, right, it's the syntax.
Okay.
Okay, so it's probably preserved there. We don't know. See, a lot of these areas are intensely rugged. Okay, it's, first of all, you must understand that we are very, very close to the international border. So there's no access and nobody really goes there. So Somorari was first, like I said, identified in 2001, and then subsequently there was a DST sponsored field workshop in Tibet, in Ladakh. And there was a team of scientists or a team of geologists that went, and then they reworked on those samples. But a lot of this part is completely not worked on. Nobody has gone there.
What's the syntax?
Maybe he'll explain that better.
Syntax was seen at first as the place where you have the edges of the ancient continent, the corners, and the edges of the syntax. So that's one way to look at it. But then if you think about another way to explain it, which is that tree, then it's also another way to use the syntaxes around the rigid object of the individual tree. But these are places peculiar because then in terms of deformation, then you can expect a point where you have more insulation, more pressure, in terms of it's different than the linear belt.
The proximity is so close, and why are we not finding the same stuff? Should
Like the other side.
We don't know. They may be. We've not. Nobody has checked. Maybe. Yeah, Namche Barwa is also. I don't know if it's here, but yeah, the Namche Barwa is here. Yeah, right. There also you find.
In the suture zone, it marks the syntax because it marks the collision between the Indian and Eurasian plates. Is it?
The Indus suture marks the contact or the suture.
Yeah.
It's not the syntax. Okay, we'll stop. We'll take a break and come back. Thank you. Yeah.
Can you play the videos?
Yeah, I'll tell you
At the end.
at the end, yeah. Is everybody there? So let's finish our journey. Oh, you see? No, no. Ah, okay. Across the Alpine Himalayan belt, so after looking at the Western Alps orogenic wedge, no, I want to the other one. Sorry, that's the should be Aegean, so it's this one. Yes, and the next one is just after. Yeah, we're going to continue our journey through the Alpine Himalayan belt and finish the story on the Aegean that we started yesterday. So we went through that. Convergence, slab retreat, tectonic accretion of tethyon units, high pressure, low temperature metamorphism, recorded in rocks of the Aegean and the Cyclades, and then exhumation back to the surface in a context of slab retreat. So that's similar to what we've seen for the Western Alps and what Malika described in details this morning for the Somorari Nappe and the eclogites, burial exhumation. That's only part of the story. We saw with the Himalayan belt that there's then a high temperature overprint on top of this high pressure burial exhumation history. And the same is seen in the Aegean with these red crosses. Not these reds are plutons. These are granitic plutons. But these red crosses are places where you have migmatites at the surface, so high temperature, mid-pressure rocks. So we're going to move to that island, Naxos, which has preserved the best structural section going from high pressure to high temperature. So it's a good place to test how we go from one to the other, to characterize it. So this is Naxos. Very nice place to work, not too much vegetation, nice food, nice people. It's easy. You have some climb, but not so much, so it's a very nice place to work. So the island is about 40 by 20 kilometers in size and is dominated by schists and marbles. So this is the Mesozoic sequence, carbonate sequence of the margin of Eurasia and also the one of Gondwana. That has been tectonically accreted in all the Alpine Himalayan belt, right? It's the same. And these marble and schists, they have preserved high pressure, low temperature metamorphism dated at 50 million years. No, not so far from the one of the Somorari, right? So the same timing. And it's preserved in the southern part of the island. But then these rocks have been overprinted by a mid-pressure high temperature metamorphism that grades from green schist facies in the south to amphibolite facies in the core of the island. And it's in the core of a migmatite dome that I'm going to describe in details. So you see these zones 1, 2, 3, 4. These have been mapped, and these lines actually. These are these isograds: biotite, chloritorid. Sorry, I should start with corundum, biotite, chloritorid, and then kyanite and sillimanite. So you have concentric isograds that have been mapped in this area. So you have marble and schist, their metamorphism, and they've been intruded by a granodiorite Pluton dated at 11 million years. And that granodiorite Pluton is probably if we refer to the subduction, it's probably the time at which the slab retreats in such a way that it's at 100 kilometers beneath that island at that time. And this intrudes the schists and marbles and cross-cuts the isograds. So it's post-metamorphic, or part of the metamorphism. And then all of these rocks, plutonic metamorphic, are juxtaposed along low-grade units and even sediments in yellow, sediments that are conglomerate sediments, detrital, coarse detrital, along a tectonic structure, a marionite, which is very low angle. You know? If you take it in the north-south direction, and that's the cross-section north-south, it's except for it's going around the dome like this. And it bears a lineation that is northeast, southwest, and kinematic criteria that tells you it's top to the north. But this detachment has a very strange shape, going from like this, goes around the island, and you find a little piece here on the other side. So at the same time, it's on the north-south section is not too much deep. The dip is fairly shallow, but on east-west section, it's folded. So we call it corrugated. It's like that. Okay. So we're going to address the two questions: how we go from high pressure to high temperature, and what controls the dome formation. Dome formations, there are several models that have been invoked, either fold interferences with shortening direction that are perpendicular to each other, and that will lead to a map pattern like this, with shortening like this and shortening like that, either at the same time, so that's folding in 3D, or successively in time, like this and then like this. Another way to produce domes is by diapirism, gravitational instabilities. And the chance we have in Naxos is that everything has been proposed. So we can then address these different models and look at what were the evidences provided by the different researchers. The first that worked there, they mapped the isograds. That's Jensen, smart Dutch guys, that went into the Cyclades for geology. He did the geological map of Naxos, and he mapped the isograds, and he could show that the isograds are concentric and centered on the core of the dome, which he interpreted as being related to a dome up, and that might be related to diapirism. Another option was proposed just afterward by Gauthier, that the detachment might be playing a role, and it's then a 2D view of dome formation. Is really an antiform that should form in this sequence. And the idea being that beneath this detachment, the ductile crust would be exhumed and forming an antiform. It's not really a dome, that's an antiform. So it explains the antiform shape, but not really the dome in 3D. But it's in a way to connect the detachment with the structures that are underneath. So these guys proposed that there was two directions of shortening, concomitant with stretching in a northeast-southwest fashion, and that might explain the domes. So I'm not going to go too much into details of that, I think. Yeah, these are the evidences of folding that we find. We find the folds. Extensional, compressional, so that starts to be confusing. It's, okay, we have shear zones, normal folds, shortening, compression. So yeah, it's confusing. So let's go with how we address that question. So first we did mapping, and we identified that actually this at first sight might look at monoclinal. No, it's marble schist. It's actually folded 3 times. No, F1, F2, F3. As we saw for the Lavrio. And these are actually the folds that have been described. So maybe I should go through that. So there are isoclinal folds, but there are also upright folds. And here in that work, they've been taken at the same level. They say that upright folds are equivalent to isoclinal folds, overturned. That's not true. No? These type of folds, they form in a hot environment with ductile rocks. These type of folds, these ones, the upright ones, they are mostly related to buckling, not to flexural sliding. So you don't want to mix folds like that with isoclinal folds like this. So again, by going back and forth from the scenery to the panorama to the outcrop, then you manage to identify F1 printed by F2, and then upright folds at a large scale that are F3. So that's a schematic representation of that. And these folds that we see here in the scenery, you see that they are rotated by the dome. So what is the relative timing between folding and dome formation? The dome occurs before or after the folding? After. Huh? After. And the dome, see, it's consistent with also the folding of these detachments. So that's where there starts to be it's difficult to set up the relative timing. And what was the surprise in these rocks is to identify what we call second-order domes or subdomes. So within the main dome, there are other domes, and they are delineated by marble layers that show second-order domes within the first-order dome. I think I didn't put the things right in the order I was starting to think this morning. So I have my story a bit messed up. Okay. So that's here a section that has been done parallel to lineation, perpendicular to the detachment, in order to check from south to north what is the history of cooling and exhumation, making the assumption that cooling is related to exhumation, having material points going closer to the surface. And this has been done by biotite, white mica, and hornblende using argon-argon. So that's allowing to build the temperature time history. So I reached to that with the Western Alps, but I didn't tell you much of the details. we can do temperature time using Hornblende is typically 500 degrees Celsius for argon-argon. So that's what we call the closure temperature, at the time at which the argon produced by potassium decay is trapped into the hornblende. And you need to find, in order to date with argon, you need to find minerals that contain potassium. And hornblende contains potassium. Biotite, muscovite, it's typically, muscovite is 350, and biotite 300 degrees. So if you analyze the argon for hornblende, muscovite, biotite, you might build, get an age for each of these systems. If you're lucky enough to have in the same outcrop this diversity of rocks, then for a single point you can have the temperature time evolution. And this is what has been done here on several outcrops that were taken from a distance to the detachments that is almost outcropping to the north. So from 0 to 30 kilometers away. And you see that there is some kind of a trend, with hornblende being typically older than white mica, and white mica slightly older than biotite. So it makes sense. You have, for one point, in material point, you have systematically hornblende older than muscovite, older than biotite. And then looking on the north-south section, you see that the age are younging towards the north. So that's consistent with having exhumation earlier in the south and cooling earlier as the detachment was active and exhuming rocks first in the south and then in the north. I think it's a very nice demonstration of that. Did you follow? So the story, keep in mind that it happens from 16 to 12 million years. That's about the time of the granodiorite emplacement. It's about the same age, and actually the granodiorite has recorded magmatic textures in its core, and then CS fabric on the edge that grade into cataclysite. So it's ductile to brittle. And that has the same logic of going from hot to cold as the rock is exhumed. So now we're going to go across that metamorphic gradient with different samples from here, this, which was called zone 3 by the isograd map of Jensen, and then we move towards the migmatite. And this was an important step. No, before that, it's no longer the case, I think. But let's say that the first approach in this type of environment was to take samples in different metamorphic zones and pretend they represent a single material point in space. But here we have an island which is 40 by 20 kilometers. Could we consider that as a one point, one material point? It's difficult, and we will see that it's not the case. So then people would get PT from zone 3, PT from zone 4, PT from zone 6, and then build a single loop. Say, okay, that's the PT path for Naxos. Okay, the assumption is that this entire island behaved as a single block, rigid, in PT space. So what if we challenge that assumption, and when we take samples, different samples, and check the PT record? So that's the same, and I'm glad, this program is very well organized. So Malika has shown exactly how she did it with the Somorari eclogites. So we did pretty much the same thing. We looked at the mineral assemblage, which was in contact with which. So here garnet, fengite, plagioclase in this rock of zone 3. So we can, thanks to experimental work that have calibrated these reactions in the lab, then we can say, okay, we have this mineral assemblage. That means that we are in this zone. And in this rock, there are metamorphic reactions that are shown by coronetic textures, coronas, with garnet going into muscovite chloride going into garnet biotite, which documents two different mineral paragenesis. We call paragenesis the minerals that are in equilibrium, and documents here isothermal decompression. So let's see if you are on the good tracks. What does it mean in terms of tectonics? Isothermal decompression. What does the material point? Decompression. Exhumation. Subduction is the first step to bring that sample that was a sediment to high pressure. That's increased pressure. And then decompression, exhumation. And it's isothermal decompression. So this will reach to the next lecture, the last one on this Phanerozoic belt. It tells you that the temperature didn't change during exhumation. What do you think? Is it calling for fast or slow exhumation? If the temperature doesn't change. Okay, I'm not going to answer that. It's not, you're not there yet. That's fine. But we here see that it's isothermal decompression. Okay, let's move then now to the next exhumation. To the next sample, 4. Here we have staurolite, biotite, kyanite, which is consistent with this field. So it's not very well constrained, but this field in the PT path, which is slightly higher temperature than the previous one. So this point has been submitted, and it's at lower structural level compared to this foliation, and it has encountered higher temperature. And then it's been put back in contact with this one, so they have followed the same path of exhumation. So the fact that the sample 4 that is below 3 is higher temperature, what do you think? Does it logic? See, it's not really higher pressure. We don't really know, we don't have any insight on the pressure, except that it's within that range. But we don't see that decompression here. We can draw that line across it. Well, the idea might be, if it's deeper, it's higher temperature. That makes sense. At the time, and these are the minerals that are in equilibrium with that foliation. We're not talking about the F1 folds, it's the S2 foliation. Then zone 5, here, just at a lower structural level compared to 4, a slightly higher temperature. Well, we follow the same logic. The deeper we go, the higher temperature we have in the rocks. Okay, let's move now to zone 6. What do you expect in terms of temperature, pressure? Higher temperature. And so lower pressure. This is correct, this is what we found, but we were surprised at first. Why lower pressure? It should be, as we go down structural level, we should have higher pressure, right? So this, at first, it was not really intuitive. But we'll see. So that's 6, sillimanite instead of kyanite. You see the sillimanite here. In equilibrium with another type of garnet that is also constraining the PT, mostly the temperature for the garnet. So we have lower pressure for a sample that is coming from lower structural level. Okay, maybe the way out is that these rocks are migmatites. These didn't show any sign of partial melting. These are migmatites. So most part of this history recorded in these rocks is no longer preserved in these rocks because of melting. And really, I think what you record in these migmatites is the time at which they crystallize. It's not the prograde, it's the retrograde path. And if there are no minerals, there's no record. So it's the time at which these rocks crystallized. And what it tells us is that between the time at which this rock has recorded its peak pressure and the time at which these rocks have crystallized, there has been decompression. So there has been exhumation. And it's relative exhumation of these rocks compared to these ones. So there has been a motion of these rocks closer to the surface compared to these rocks. So you see that, you're starting now to play with different surfaces, material points, things that you can hold in your hand, and then surfaces that are immaterial, the surface topography. It's ever-changing, it's not a material line. And isotherms, these are also lines that go across rocks. These are not material lines. So then, your brain starts to be a bit getting hot, because you have to play with material points moving relative to the Earth's surface, burial exhumation, and then isotherms moving relative to the material points. That starts to be tricky. And then you have time. And time I didn't put now. Okay, I forgot this story. Yeah, at first, these rocks, the migmatites, so this is our new map. These rocks, these migmatites, were considered as being a basement, very scant basement, compared to the Mesozoic platform sediments. And it's something that is very common in any type of maps. Maps usually, and stratigraphy has been done on sedimentary rocks, following the stratigraphy. So you go from Cenozoic, Mesozoic, Paleozoic, and that was the work of Werner that I mentioned in the first day. As long as you could find some way to identify the sediments, it was easy. And as soon as these guys got into gneisses, off, basement. Which is fair enough. They are lying underneath, so basement. But the more we look at these rocks, the more we realize that they are younger than the sediments. In terms not of protolith, but in terms of metamorphism and processes, deformation, and so on. So, basement. And in this basement, what do we see? Blue. Blue is marble. Just from the map, you have something that is strange with this interpretation cover basement. What do you think? The blue is into the basement as big chunks. Is this consistent with the cover basement relationship? Not too much, huh? So the people, they saw that, huh? So they said, okay, maybe the cover has been infolded with the basement. And now we see a section like this, and we see cover that has been put into the basement. That's one way to do it. But okay, how to test that? Well, look for the contact between these marbles and the host rocks. And first, we looked at the contact between the migmatitic gneiss and the paragneises or the schists that are in brown here. And what you see here is that, what do you think? You go from brown to white. The brown is biotite rich, layered, foliated rocks. Can you see the leucosomes here parallel to the foliation? So concordant leucosomes. And the more you go towards the left here, the more you are, the more quartz feldspar there is. And this is mapped as the basement cover transition. I think from what we see here, we can also propose that here there's a gradient of increasing leucosome, increasing granitic part, which might be interpreted as a gradient of partial melting. Still leaves us with a problem. Here it's more quartzo-feldspathic. If it was the same photolith, it's more quartzo-feldspathic than here, which is more iron-rich, iron magnesium-rich with the biotite. So where does the iron magnesium go? Well, first part of the answer is that we have lots of garnet in here that might incorporate these elements. And it's probably not the other way out, and it's an easy way out, which you cannot test in that outcrop, is that, well, the system, as soon as it went from metatexite to diatexite, which is what we see here, then became open. So we lose minerals by segregation, melt crystal segregation. I see your face. It's an easy way out. Huh? Say, okay, I've got a solution. I put the dirt down below the carpet. But we're going to see that it's not that stupid. So what does it look like inside the dome? Migmatites, with different types of migmatites, metatexites with leucosomes concordant, diatexite with lots of enclaves into heterogeneous granite. And it's surrounded by leucogranite. It's highly deformed only on the southern edge. And if you look at the microstructures, it's not a pristine magmatic texture. You know, it's kind of grungy. If you look granite with a magmatic texture, you see uridral crystals, interstitial crystals. This look like more grungy. And probably my intent now is that part of these minerals are residual from the photolith, part are crystallized from the melt, and part might be peritectic minerals. Peritectic, maybe not everybody knows that, that term. The problem with the melting reaction, if you take, let's say, quartz, feldspar, biotite, aluminum silicate, for example, sillimanite, a typical reaction, it will go to melt plus garnet, for example. And the only part that was liquid is this. So you might have, if this reaction is partial melting, then you might preserve part of these residual minerals. And as a product of the reaction, you will have this peritectic mineral. Garnet could be, actually, feldspar could be one of these. K-feldspar, plagioclase could be. So it could be plagioclase, it could be K-feldspar. And when you're looking at this rock from the outcrop, you say, okay, this is mostly, or even better the previous one, this is mostly granite. But maybe it was not 100% crystallized from the melt. I might come back to that later if you ask. Okay, and then there's only slight hint of high temperature recrystallization that is shown by this undulatory extinction of quartz. That means that the quartz grain has been a bit like that, and its crystallographic orientation is a bit torqued. So that's why it shows undulatory extinction. And when you have bands of extinction like that at 90 degrees, or that are like this, making a sort of chessboard, that means that there are several gliding system, slip system that have been activated, and that's reproduced in experimental work and a test for deformation at solid state at around 600 degrees. So we know that has been a hit of solid state deformation, but not much. Okay, so yes, so at first sight it might seem difficult to measure that, but we tried it. Okay, it's not as precise and when you are in the sedimentary rocks with a nice bedding, but you can measure the general attitude of these, the general attitude of that foliation, the fold axis, the fold axial planes, the sort of the envelope of the folded layer. All these we measured, And this was the work of Seth Kuchenberg. And he measured all sorts of structures. And here, these two sets of lines, okay, maybe I'll explain that too. The dark lines are measured from the field. And the red one is measured from on samples that have been collected in the field. And it's the magnetic structure, the magnetic foliation. In other words, it's provided by the orientation of magnetic minerals. So we wanted to compare both of these structures. It's not perfect, the match is not perfect, but at first order it works. So then we have measurements. And the idea then is to draw what we call the foliation trajectories. You draw the trajectories by extrapolating from your measurements. And so on. So if you're doing basic mapping, that's what you should start to do, is take a lot of measurements, as much as possible, and distribute them, and then you can start to draw the trajectories. So Thest did a wonderful job. It spent 1 month taking measurements on this area, which is about 10 by 20 kilometers. What went up and down, took about 600 samples for the magnetic foliation. And this is the map that came out of it. The first panorama showing the subdomes, it was by eye, just looking at this, I did like that. I thought, okay, I see it, but I want to demonstrate it. So this guy did the tedious work, and you can see one here, another one there, one there. Yeah, this shows with the magnetic, that's the magnetic fabric, and it shows also these rounded features. He did lots of cross sections. And then we came back to this early hypothesis. Are these reflecting polyfolding, diapirism, or another hypothesis that came into play is isostatic flow beneath the detachment as correlated with the activation of the detachment. Let's see. Because I think I've got the most schematic. Yeah, that's the most schematic view of it. Easier to see. We see drew here concentric lines to show the different patterns of the foliation. So what do you think? First, remember that we have in the mantle sequence here compared to the dome, we have fold F1, F2, F3. Do we find this fold pattern in these structures? Maybe here. Here you see that the contact between the pink and the brown is folded. So there is something to it. Do we see the effect of the detachment? Actually, maybe here. There is this trend here with the magnetic foliation that is diverging compared to that triple point. And that might be the effect of localized deformation. But other than that, within the main or the first order dome, we see subdomes, at least 4 of them. Does it match the isostatic flow? In which case, we should see 2 subdomes separated by a high strain shear zone. So we have a high strain shear zone in middle, but it would mean that there is 2 domes on each side of that shear zone. I think, from my perspective, we see here more subdomes that are independent to each other, not only related to that high strain zone, and they share a similar envelope, which is the first order dome. So my interpretation is that we have something that is more looking like that, with a single envelope for all the subdomes that are contained, no cross-cutting relationship between the domes. So if you had polydiapirs, you'd expect one diapir, and then another one, and then another one. They should be cross-cutting each other. They seem to be sort of concentric. So I think this is a better way to represent it. Okay, so that was the structure into the dome. Now I just want to attract your attention on another tool that might be useful in that type of terrains. And Deepak should listen to that. I see that he's going. You should listen to that, unless you have to go. Dikes. So these are the marble and schist with a lot of dikes. Dikes everywhere. All the white stuff sticking out are dikes. And looking at them, well, we didn't pay attention to them at first, and then we thought, okay, maybe we can use them. So we start to measure dikes, and we realized that most of them, the dikes that are pristine plutonic magmatic fabric, they were either parallel or perpendicular to the lineation. So here it's a plane of the foliation, and the lineation is like this. So you have either dike perpendicular or parallel to lineation. So this corresponds with what we call chocolate tablet structures. Chocolate tablet forms when you have one direction of shortening, and in the plane of flattening, you have two directions of extension, of stretching, sorry. And it will result in chocolate tablet. The way I looked here 20 years ago. Don't laugh. I like these ones. These two dikes, they almost met. It's very romantic, but they never met. So these are the dikes on this side. So you see the foliation is like that, and the dike are cross-cutting this way. And this one is almost not transposed and has a magmatic fabric. On this other side here, you have the foliation like that, and the dikes are like this. So it's like that. So what it means, or one way to interpret that, is that this foliation had been already tilted before dike intrusion. Tilted towards the east in the east, towards the west in the west. What if we look now more carefully in these schists? They're actually full of dikes. Half of the rock is not schist, is dikes. But dikes that have been folded. So, at first sight, you don't see it. And once you start to look at it, then you find them. And you see the relationship between the folded dike, transposed dikes, and the ones that are magmatic. So what does it mean relative to these dikes? They intruded before rotation, before intrusion of this one. So then you start to build a story of deformation, magma intrusion, deformation, magma intrusion, and transposition. So we measured everything. And here, for example, we have a sheared dike, another folded dike. And that's for the east-west section. What happens in the north-south section? Well, the same. Dikes that are vertical with a magmatic fabric, but other dikes that are sheared. So it's not transposed here, transposed there. This dike is the same, so it corresponds to a single magmatic emplacement. So probably we have here a strain gradient, a shear gradient, or deformation, strain gradient I think is the best. And here this the schematic is consistent with top to the north, which is the main kinematic recorded throughout the island. And it's true on both sides, on the northern side and on the southern side, the dikes are all transposed top to the north and cross-cut by magmatic dikes. So the idea then came out to use these dikes as markers of deformation through time. So if you look at the plane parallel to lineation is like that, and that's perpendicular to lineation. So parallel to lineation, the first dikes are like this, and then dome starts to form. Sorry. And what this is also showing is that it records deformation and magma emplacement during dome formation, during tilting of the foliation. So the first step, these dikes that are then transposed sheared to the top to the north, and then cross-cut by new dikes that are going to be transposed and so on. And so that's on the plane parallel to lineation. Perpendicular to lineation, what we see is predominantly shearing towards the west on the west and shearing towards the east on the east, which is consistent with migmatite up. And you have on the top, where we could find some dikes on the top, either on the north or south, it's usually pure shear on the symmetric axis. So here's the sort of a cartoon model that I built. Is a first generation of dikes rooted in the migmatites that were emplaced before tilting of the foliation, and then after tilting of the foliation, the second generation of dikes, or there are many of them actually, it's not one, two. So what would be the next step if we want to go further? What would you want to do if you had money and an analytical tool to go further? Deepak, what you want to do with your dikes? Want to sample them? Look at the chemical evolution. If it reflects some kind of fractional crystallization, or it reflects partial melting at the source, you know, do they reflect differentiation? And also, if you sample, that's what we did, we sampled the most transposed one and the least transposed ones, try to date them. Then you have the timing of the process. And we were lucky, got an age of 60 million years on the most transposed dike, 13 million years on the least transposed one. So it means, and that's beyond, that's significant, this difference is beyond the error bar on each of these ages. And you see the bell curve, these are the ages, number of dates as a function of time. So it's fairly consistent. So it means that this dike transposition occurred within 3 million years. And it gives us the timing of dome formation within 3 million years. I like this one. That's the Möbius, you know, the Möbius torque, or no, doesn't. It's a very peculiar feature. Look at these dikes. Here they looks like it's cross-cutting. This one is cross-cutting this one. But if you follow this one, it roots into that granitic pocket. If you follow this one, it's folded and roots in the same granitic pocket. So how do we interpret that? Here you say this one is after this one, but they are in textural continuity here. So they come from the same magma pocket. I think the way we have to take that information is that, well, magma emplacement is not like this. Deformation, which causes transposition of this one, is not like this. Takes time. There's a time for magma crystallization. There's a time duration for deformation. And that's, there we got in trouble. We got in trouble because when we go to the geochronologist guy, they want to have the time as precise as possible with the smallest duration. And us, tectonics person, we say, okay, I want to date something that has a duration. It's incompatible for now. So I think we need to find clues to match these two different motivations. So I'll come back to that in a few slides. This geochronology tectonics difficulty. So the conclusion here, we have a dome with subdomes, a lineation that is dominantly northeast, southwest in the migmatites and in the metamorphic rocks around. But around the subdomes, actually the lineation is radial. So you have two processes here that are controlling the structures. You have probably the regional scale tectonics, which is related to northeast, southwest stretching, folds, and so on. And then a logic which is proper to the migmatite, to the partially molten rocks, which develop their own mechanics with subdomes into a larger dome, probably related to buoyancy, with an imprint of the regional tectonics. It's not saying that it's not happening. Actually, the first order shape is an ellipse. It's not a circular dome. And here you see that the contact is folded. It's been also sheared. So you have a bit of everything, but in the center, it's mostly, I think, buoyancy-driven subdomes. So let's now look at the zircons, and we'll come back to you, zircons in the migmatites. So this was done by, I lost a reference, but it was our first PhD student with Stéphanie Duchesne, who's the person I worked with in Naxos. And the challenge that we gave her, I'm not sure how I'm doing with the time, but the challenge that we gave her is to date metamorphism, which is still a challenge today. It's not that easy to date metamorphism. We can date crystallization of accessory minerals. How does that relate to metamorphism? It's not a one-to-one relationship. You need to date minerals that you can be sure that they are implied in a metamorphic reaction. But I'm going to do it short. So she found the zircons, and some are very grungy like that. That's terrible looking zircon. You don't want to date that. But in those, she had, and this porous zircon full of inclusion is interpreted as being related to dissolution precipitation. So it's disturbing the uranium lead systematics. But they have here a nice overgrown, zone, oscillatory zone, and that we can get an age out of it, which is 17 million years. Other than that, we have pre-seen zircons with nice zoning, but when you date this, 300 million years, Variscan. But you see that here, this nice zoning is cross-cut by another zone here. And when we did the analysis here, going from the inner part to the outer part, we get 24, 22, 19, 17. And at first, Laure Martin, who was doing that work, said, okay, all this is part of the same, they are slightly discordant. We consider that they are part of the same age. All these dates, his point here is a date obtained by ion beam. You should have stopped me. Do you know what this is? No. Okay. So we take the rock, we crush it, separate the zircons. Zircons are rich in uranium, and then that will decay in lead, so it's perfect clock. So we separate them, and then we put them into epoxy. And after that, we abrade the zircons to be able to see the interior. It's very important because then you see the texture. And with the ion beam or with a laser, see that's here 50 microns, we are able to do holes of about 20 microns. That's the best we can do at now. We cannot go much down much smaller because then we lose resolution. And we ablate the zircon, take out all the uranium and lead isotopes, and everything that is there actually, and then separate these isotopes in the mass spectrometer. And you count all the U 235, 238, lead 206, 207, and 204. And then this allows you, as you know, the decay of uranium into lead, this leads to an age. It's actually, we call it a date. A date is like, it's a data. And then we try to make sense of that, which we call an age. So these are the dates. And as we have two different systems, we have the 235U and 238U that decays both of them in two different leads, then we can have two ages that can match. If they match, they should be on this line. If they're a bit offset of that line, that means that there is some lead loss, and that will change one of these ratios and will offset the data point from the line. So these data are almost concordant. We call them concordant when they are on this line, but not so. So Laure said, okay, I take all these, the dates from 24 to 16, and consider it's one age. And when you do that, when you do the statistics, these are the analytical points. Right? Each of these ellipses translate into 206, 238 age, or date, sorry. So that's each of these spots. And the average of that, when you do the statistics, is this green line, which gives 18.7 plus or minus 2.4. That's the average. And then you can calculate a mean standard weighted deviation. Are you familiar with that? Huh? Which here is 65. The mean standard weighted deviation is a way to test if all these dates correspond to a single age. In other words, all your data points, n, should have a bell curve distribution, and you shouldn't go beyond the 2 sigmas that you consider for your main standard weighted deviation. And if this is the case, that means that the error on each date is smaller than the 2 sigma, then you should have a mean standard deviation, weighted deviation of 1. So here already, something is not matching, 65. When you look at the red lines compared to the green thick line, what do you see? Well, some of the dots are not even covered by the average. So maybe there was something wrong with this date, with this analysis, or maybe it's because it doesn't fit the assumption that we made at the beginning, that all these dates correspond to a single age. Maybe there are different ages there. And this is what we explored afterwards. Say, okay, maybe that trend is significant. It's not part of the same event. And each of these dates corresponds to a crystallization event. And there we lost the geochronologist. He said, okay, no, I'm not following you on that ground. Okay, fair enough. So I made some statistics on groups of dates that could relate to each other and are overlapping. So then we have 16.6, 18.5, 22.1, 24.2. Of course, we need more points to be more reliable. There are not enough points here to do the statistic in a good way. But from that, we can gain that instead of having a single age of crystallization, we probably had several steps of dissolution precipitation, because here, this type of texture reflects dissolution precipitation in cycles of 1 to 2 million years. And you see that here the record is totally different. These are the same dates, and they all overlap. And here, the statistic, I think, is pertinent, because you see it allows, compared to the error margin on each date, it allows to refine the age, and the mean standard weighted deviation is 1.1. That's perfect. So that means that all these might be interpreted as representing one age, same age. 13.3 for this one, 16.1 for this one. And note that the transposition of these dikes is from 16 to 13. So I insisted on the duration, 3 million years, but compared to these dates go from 24 to 16. So it's before. So you had crystallization of zircon in the core of the limatite before transposition of the granitic veins. So these are not exactly the same timing. So how now we're going to put that into a single framework? And that's actually where we lost the geochronologist there. He gave me the idea, because these cycles of crystallization of zircon had been identified by the first person that worked on geochronology in this island, and she proposed that the isotherms were moving relative to the zircon, up and down, and related to fluid circulation, to hot fluid circulation that would cause this sequence of event of crystallization of zircon, which is a good hypothesis. But when we checked, we didn't find any signs of hydrothermal alteration, neither in the zircon nor in the mineral paragenesis. And if you play with thermal models, to crystallize and dissolve zircon, it's at least 800 degrees, even maybe 900 degrees that is required. And to play with the 900 degree isotherm, it's not that easy to go up and down in the crust. So it takes time. and we come back to that just later on, takes 20, 30 million years. So it's not like 1 million years. You know? So the geochronologist said, oh, but it's easy. If it's not the isotherms that are moving relative to the zircon, maybe it's the zircon that moves relative to the isotherms. He told me that like that. I say, wow, brilliant. That's the solution. He said, okay, I don't understand. You just described convection. I said, oh, I'm out of it. He said, I'm not following you on that ground. No, convection at the crustal scale. I say, well, if you don't believe it, that's your problem. So let's try now to prove it with physics. Because, I'm sure here there are very different cultural background, religious background, and once we come to religion, then there's no use to discuss. We are doing science. So if your religion says that convection is not possible, then I'm not fighting with you. No. So I didn't go to religion, I went to physics. So I asked my colleague physician, okay, what would be required for a crust that is that is partially molten for about 20 kilometers? What would be the condition for having it to convect? Well, if you take a viscosity of 10 to the 18 to the 17 Pascal seconds, which is fairly conservative in terms of what we know about partially molten rocks, then it works. We have a Rayleigh number, which allows to assess if the system is in convection or not. That is over 1,000 for a crust that is partially molten, or layer that is partially molten for 10 to 20 kilometers. And the Rayleigh number is considering the difference in the density, rho, the thickness of the layer that is considered, the heat production, H. Oh, sorry, beta is an expansion, thermal expansion. And here is D so D is very important. That's the size of the system. It's D power 5. No? So if you take, and that was the same computation that Holmes did for the mantle convection. He took exactly that number. So you can do it either by heating from the bottom or heating from inside, but it gives the same type of results. Convection is possible. So it went all the way that the geochronologist didn't want to publish the data with us. His choice. So that's where we went. Convection with zircon here would crystallize, then go down, be dissolved, come up again, and this several times. That's an elegant way to explain the geochronological record. So how does it go now? Okay, now compared with the dikes. So we have the early dikes. Sorry. First, convection from 24 to 16. So that lasted 8 million years. And then the early dikes start to pick up after the end of the geochronological record in the migmatites at 60 million years. And the latest dikes, 30 million years, record the timing of dome formation. So we propose here that there was a first stage of convection without doming, and then doming. That is the end, the last diapir, if you want, within that partially molten crust. Okay, let's wrap up now, taking all the information we have. So we have a first period of burial associated with the first folds, and then exhumation related to the second folds that is recorded in these rocks. Then thermal relaxation of the thickened crust, built by burial exhumation, increase in temperature. After some thinning, which corresponds to collapse, and the dome formation happens at that time. And then the last exhumation, everything for the last 5 kilometers, all these were exhumed at the same time. So put that into a tectonic scenario, a first stage of burial, and see here I also draw the isotherms. So that's also preparing for the thermal models. And we tried that early on. what is isothermal decompression, and we were not really ready for that. Huh? So let's take an example. I take a reservoir of water, hot water, put water in a bath, huh? Very hot water, and you put your hand like this. Huh? You're not going to, if you do it very fast, you're not going to feel the temperature. But if you put your hand and then wait, then it's going to be hot. Right? So what does it mean? That you have high pressure, low temperature. That means you have burial, but exhumation that is faster than conduction. Huh? You get it? So what does it mean if the temperature is increasing? That means that the rocks stay. And then the exotherms go across the rocks by conduction and heat production by radiogenic decay. So the first stage, burial exhumation, and that's preserved at higher structural level. It's preserved at the top structural level. And for the rocks that have not been exhumed closer to the surface, then these ones at depth, they start to see the temperature rise. So that's the second stage. Increase in temperature. And this is concomitant with slab retreat in the area. We know it from the surface magmatism. And then in the last stage, this thickened crust that started to heat up, then was thinning and formed this metamorphic core complex, and that's the time of doming as well. Now what's nice about the Aegean domain is that these sequence of events, high pressure, high temperature, and decompression, occurred several times. In the northern part, in the Rhodope, it occurred at 70 million years for the high pressure, and the high temperature about 30 million years after, at between 40 and 30. And 20 million years after, the same sequence of events happens here. High pressure and then high temperature. And today, in Crete, in the southern edge of that, only high pressure rocks have been identified. If we wait another 10 million years, maybe the high temperatures are going to come. You see the logic? And this is all related to construction of the orogenic belt associated with convergence, but as the plate retreats, the crust that has been thickened then thins. Okay, that's, I think, what I wanted to show this morning. What time is it now? 12:36. So we might go through today, if you're not too tired, to how we deal with these observations in terms of models. But we might take a short break maybe, because it's 5 minutes, it's fine? Huh? Because usually we should finish by 1:30, right? 1:30, yeah? Okay, 1:30. Okay, take a break, unless you have questions now, and then try to wrap up this concept in 45 minutes with models. Okay? Or do you want to keep the models for tomorrow? Depends on how we feel. Take a break? Okay, 5 minutes, okay. Yes? They okay? So that's the end of our journey relative to Phanerozoic orogens. Tomorrow we'll have a hint of Precambrian orogens. And what I want to show you is how from the Alpine Himalayan belt examples, Western Alps, Himalaya, Tibet, Aegean collapsed orogeny belt, we can think of these different stages of orogenic evolution in terms of thermomechanical evolution of Phanerozoic belts. Wedge mechanics, crustal thermal evolution, and then combining the two. This is our goal for the next 45 minutes. So we identify that plate convergence is mainly accommodated by subduction. So that's the process that we want to consider. And it results in very different type of topographic features, wedge-shaped mountains like the Western Alps, orogenic plateaus, or even intermountain basins that reflect collapsed orogenic belt. And this is pictures here, so I think you understood that. Huh? So now, let's come back to that first question we asked. What limits the altitude of the surface topography in mountain belts, in zones of plate convergence? Now that you've seen more than what you knew 2 days ago, what would be your idea? So we talked about gravity versus tectonics, erosion. Are you okay with that? There is no more than just gravity and tectonics? Isostasy, yeah. But think about what we described in terms of how the rocks involved in the orogenic belt evolve in time. They go from high pressure to high temperature. Do you think that this might play a role in terms of, yeah? But you're not so sure how. Huh? And then what controls the transition from crustal thickening to crustal thinning? Do you have ideas about that? Not so sure. Okay. So let's look at plate kinematics in a very simple way. No, I just drew that with a pen on a paper. So the first hypothesis is that this point in between the overriding plate and the subducting plate is fixed, and that corresponds to the trench. In that case, the length of convergence should be correlated to the length of subduction. Okay, that's easy. Then let's consider two different cases. The case of plate advance of the downgoing plate relative to the overriding one. And you see here that the amount of advance is not going to be subducted. So the amount of subduction is convergence minus the amount of advance. And the resulting situation is that here there's overlapping of surfaces, lithospheric surfaces. Which means, so what happens in this area? What happens to the lithosphere, the green part, in this area, if there is plate advance? Thickening, lithospheric, huh? All the green is here lithospheric. And I'm going to separate plate scale, lithospheric, from crust-mantle coupling. These are the two different aspects I'm going to treat here. So first, very simple, lithospheric. Thickening. And the other case is when there is convergence and retreat. And here this results in a decrease, or the surface loss here. What happens here to the lithosphere? Thinning. And the amount of subduction is the amount of convergence plus the amount of retreating. And in the extreme case, you see my elbows, you might have subduction without convergence. That's a nice one, no? So subduction is not always convergence. And you might have convergence without subduction. That's the indenter model. This is the indented model. So now what happens to the continental crust when it arrives in the collision zone? So collision being defined as the contact, the time at which the two continents are put in contact. So it might either go down, be coupled with the lithospheric mantle, and this is called recycling, or it might be decoupled and form an orogenic wedge, which is called tectonic accretion. So that's simple. We can put the decoupling layer in different places between, for example, the oceanic crust sediment interface, between the basement cover interface, between the lower crust, middle crust interface. There are different interfaces in the crust that might play that role, and the most likely one is actually the lower crust, either the mantle crust transition or the lower crust middle crust transition. These are very marked in terms of rheology and density. So let's say that the continent is fully coupled with the lithospheric mantle, then it subducts. And can we imagine such a situation? It's possible, actually. In Gibraltar today, it's probably the case. You have a thick crust, no topography, and a thick lithospheric mantle that is plunging. You know Gibraltar, huh? And there's a huge gravity anomaly that shows that there is continental crust there, but it's not shown by any topography. Very, very exciting situation. And it's probably a case where you have retreat without convergence, because Gibraltar, you see where it is? Yeah, you know, I'm thinking as I'm talking. Gibraltar is here. And I've got a master student retrieving the Bouguer anomaly, comparing this with the seismic anomalies, and there's no topography here. And it shows, the gravity anomaly shows a thick crust beneath that, and associated with a slab that is plunging towards the east. And conversion is like that. So there's no way that this subduction is related to convergence. So it's probably being subducting like this, but then with the retreat, went like that. And in Gibraltar, you have a subduction with lots of retreat, no convergence, and subduction of continental crust. And the other situation is that it's fully decoupled relative to the lithospheric mantle, and that forms the continental, the orogeny. So you have two parameters, two possibilities: advance, retreat, coupling, decoupling. That's a 2x2 matrix, 4-case scenario. And that's the main contribution of my colleague Stéphanie Duchesne. Myself had drawn about 12 scenarios. And she said, no, if you have two parameters that can have two solutions, it's a 4x4. It's 2x2, so it's 4 scenarios. Okay, so I'm going to reorganize my drawing, and that's what I did. So if you take crust-mantle coupling and advance, that's the indentation model, and deformation will occur mostly in the overriding plate relative to the suture. Here, with crust-mantle decoupling and advance, you have both crustal deformation and lithospheric deformation actually on the overriding plate, and mostly crustal thickening in the downgoing plate. So you have thickening on both sides of the suture. So you see, you have observables that you can test for this model. If you have crust-mantle coupling and retreat, then the upper plate is thinned, and this leads to subduction of the continental crust. And the most interesting part, scenario, is this one, I think, where you have crust-mantle decoupling and retreat. So this pink crust is coming from this downgoing plate. So the orogeny is built by tectonic accretion of units that come from the downgoing plate. And the suture is here, nothing happens to this side of the suture. And it's pretty much what we see in the Western Alps and in the Aegean, is most of the deformation occurs ahead of the overriding plate, not in the overriding plate. And at the same time as the crust here thickens, because of the retreat, the lithospheric mantle thins. which might seem a bit peculiar. You know, we think, okay, there's convergence, everything should be thickening. Well, here we managed to find a way to explain crustal thickening co-eval with lithospheric mantle thinning. And that's not fancy modeling, it's just a drawing. Right? So sometimes you don't need a supercomputer to find interesting things. Just drawing things, putting things on scale, and think. And this is, all the parameters are converging towards hot, because you have thick crust producing heat by radiogenic decay, thin lithospheric mantle, so a thin conductive insulator, and thick crust, so high topography, thin lithospheric mantle, high topography. So everything is joined to have a hot and buoyant wedge. And it only waits for something to collapse. And the data that we can confront these models with are the position of the suture relative to the orogen, the crust lithospheric mantle thickness ratio, surface thermal heat flux that might be also recorded by metamorphic rocks, and topography. So I showed already this to show that here in red, these are the places where the lithosphere is the thinnest. So throughout the alpine Himalayan belt, the lithosphere is thin, and the crust is thick. This situation is the prevailing one. And most of this is consistent also with high surface heat flux, thermal heat flux, that is probably caused by a combination of a thick crust plus a thin lithospheric mantle. So let's now synthesize the PT path recorded by different rocks that we've seen in the Western Alps in blue. So burial exhumation. The Cyclades, burial exhumation, the Northwest Himalayas, burial even deeper, isothermal decompression, and a hint of thermal relaxation, increase in temperature, and then final cooling and decompression. And for the Cyclades, for some rocks, high pressure and then isothermal decompression, and some rocks, same path as for the Himalayas, increase in temperature and exhumation. Except that the Himalayas are still thick and the Aegean is thin. So this we call burial. Thin orogenic exhumation, that is the most counterintuitive one. This isothermal decompression related to these high angle detachments contributes to construction of the orogen, not to destruction. This is how the decoupling accommodates construction of the orogen. And then thermal relaxation, and then collapse. Post-orogenic exhumation, that's related with these low angle detachments. So you have to distinguish between these different types of shear zones. So in terms of thermal evolution, just first, again, very simple, just graphically. Take a 30-kilometer crust to start with a geotherm in red, with less than 600 degrees at the beginning, at the moho, and take this point and instantaneously put it at 60 kilometers. That means that crustal thickening is much faster than heat conduction. So this will not change the temperature of material points that are depicted here by A, B, and C. The temperature points will be exactly at the same isotherms. What will happen? Well, the pressure will increase. And that's shown here. The first step in this PT path is increase in pressure related to fast crustal thickening compared to heat conduction. And then, if you let that crust produce its heat by radiogenic decompression, the decay, and conduction, which we'll see with more fancy models takes 20, 30 million years, then you have this path, this part of the path. So the isotherms will go up and go across material points, so a point will see an increase in temperature. So that's the thickening history. Now take that thickened and thermally relaxed crust and instantaneously, very rapidly, thin it. So you take this point and you put it back to 30 kilometers. Take this point with its temperature and put it back to 30 kilometers. So the points here will be coming closer to each other, thinning, vertical thinning, and they will keep their temperature because we consider here, no, it's the extreme situation whereby thinning is much more rapid than heat conduction. So that will lead to this part of the path, decompression of all these points, but at the same temperature, isothermal decompression. Isothermal decompression. And then temperature will relax, and that leads to cooling. And some, no, this is very caricatural. This is really the end members. And in nature, it's mostly more diffuse, and these transitions. So I'm going to skip that. This is the detailed work of this proper thermal modeling, considering thickness of the crust and thickness of the lithosphere, the isotherms at the beginning, a heat production in the upper crust only, and he modeled the way the isotherms behave with time. And you see here that's 0 million years after thickening, so instantaneous thickening, and then it takes time from, so that's the initial, sorry, I should start with the red. The initial geotherm is here, instantaneous thickening, so it leads to decrease in the geothermal gradient. And then, as radiogenic decay proceeds, and as conduction proceeds, you have the yellow one, then the green one, 40 million years after. And in these models, it also has some thinning by erosion. So that explains why first the temperature increases and then it decreases. And it comes back to equilibrium state by 100 million years. Here, the brown curve. But I think the most important one to remember here is the fact that you have first, from red to blue, a decrease in the geothermal gradient, high pressure, low temperature rocks, and then an increase in temperature all the way to 60 million years, and that's the thermal relaxation part. And it takes tens of million years. Of course, it will depend on how much you put in terms of radiogenic decay. 2 microwatt per cubic meter is the correct number, I think. It's representative of most rocks of the continental crust. But 0 for the lower crust is probably a bit too low. So in other words, this is probably a minimum. So he played with other type of parameters, for example, varying the heat production from 1 to 4. So it's huge, right, the effect. And 1 to 4 is the range of heat production that we can expect in continental crust. So we can go from everything from 400 degrees to 800 degrees or even 1,000 degrees. So you can play with this to change the geotherm. Here he played with the erosion rate. So if there's a lot of erosion, then you never get to high temperature. If there's low erosion, then it allows for the crust to increase in temperature. Can also play with the initial lithosphere thickness. See, it doesn't play much role. But it didn't play much, it just changed it from 50 to 70 kilometers. In our case, it's probably more extreme. We go from 100 to maybe 20. It play with strength, strain rate, we don't look at that. And I'm going to skip that too. So we did the same exercise with my colleague, Stephanie. Yeah, just to show you, we have also the variation of the temperature at the base of the crust. That might be all the way from 200 to 1,000. So in the case of a thin crust with a thick lithospheric mantle, that's where we get. With a thin crust and a thin lithospheric mantle, we can get that much difference. So that will be, if we consider a crust, that's what's considering a crust of 10 kilometers to start with. If you take it at 60 kilometers, then you see, by varying the thickness of the lithosphere from 200 to 20 kilometers, you see here the lithospheric mantle effect. through the relative effects of lithospheric mantle and crust thickness on the temperature. But I think you got the point. I'm going to skip that too. Yeah, for the topography, you can also do the same exercise, looking at the topography in 1,000 meters compared to the crust lithosphere thickness ratio. And you can see here, taking a crust that is 60 kilometers, how much topography difference would be related to the change of the lithospheric thickness from 200 to 60 kilometers. And you see here the lithospheric effect. So it shows you that the main effect here is crustal. Okay, so now I want to finish with that, and we'll take some time. This was actually my postdoc that I did in the late 90s after my thesis. So I told you my goal for the thesis was to demonstrate that partial melting of orogenic root would lead to collapse, would be sufficiently important to weaken the root of the orogen and favor the gravity force relative to the tectonic force. And there was a big mistake in that thinking. Again, you have ideas, but sometimes they're not good. It took me 2 years to realize. So I started very simple. I took a pink layer here, that's a cross section, a pink layer, put on top of a rigid layer that was moving at that is moving here at a velocity of 1 centimeter per year on this side, and here we go from 1 centimeter to 0. And we look at the behavior of this pink layer, which is viscous, with this imposed velocity. So here you see this viscous layer, and these lines are material displacement, vectors of displacement. So these lines on the vertical profile, they go towards the west. They've been entrained by the plate underneath. And you see here, as we approach, and that's after some deformation has occurred already. Right? It's the layer started flat, and then it's been deformed as a consequence of a jump from 1 centimeter to 0 here. The consequence is that the viscous layer thickens here. And you can see here, as it approaches the zone of thickening, that the profile becomes irregular, with the main displacement occurring at the base and less at the top. And as we pass what we call here the singularity, then it's reverse. More displacement on the top, less at the bottom. This is basically simple shear. But we reach here a very interesting point. Observation, modeled observation that we didn't expect at the beginning. So if we look at the horizontal component of displacement, which is dominating here, between this point and this point, what happens? You see the norm of a vector is smaller here and bigger here. Horizontal stretching in a zone of crustal thickening. Does that remind you of something that we treated? Okay, that might be one way to do it, but remember the Western Alps today, the seismic record of the Western Alps. Thrusting at the front, normal faults at the highest and the thickest zone. And people evoke compression, extension, both. Can do that in one single event. You don't need to call upon divergence or retreat. It's going to cause that, but it's not necessary. Can explain that in a very simple way. It's just a matter of partitioning of deformation. So thickening is dominating over stretching. But why is that stretching? What is the force causing that? Because you'd think that in plate convergence, you'd have the crust just thickens. That's the most intuitive part. So the beauty of numerical models is that, okay, you're God. And you say, okay, at this time step, which corresponded, I think, to about 50 kilometers or 100 kilometers of displacement, you say, I stop convergence. Sorry, I stop gravity. In this one, I say, there's no gravity anymore. It's not consistent with the world, the real world, but we can do it numerically. I stop gravity, so I look at only the field displacement related to plate convergence without gravity. And here you see the vectors going up. And the other way around is to say, okay, at this stage, I stop velocity. So I look at the displacement field only related to gravity. And what do you see here is vectors going away from the zone of thick crust, and it's going away faster on top and slower at the bottom. So as the crust thickens, the top part flows out related to gravity. And the combination of the two, that's this. And my postdoc's boss, they were not happy with that, because they had a how do you call that, a speed car, a speed car, a very nice model, and I used it because at first I started to model, put with the idea of testing the role of weakening of the crust during orogenic evolution, and we had all the tools to do that. But here there's no temperature, there's nothing. There's viscosity very simple, no fancy rheology, and they told me, okay, you're using our nice speed car, like it was a bicycle. And we're not happy with that. You should use all the possibilities of our tool. So okay, but I did that and I didn't understand what was the result. And you guys you know that perfectly, that if you put curry and pepper and all sorts of spices in a meal, it's going to burn your mouth, but you don't know which one is burning the most, right? You have no clue which parameter is the most important if you put them all together in the same meal. So you want to sort out, okay, curry in one space, pepper on the other space, maybe, and then you can check which parameter is doing what. And then you can try combinations. So modeling, there are two different strategies. Either you want to understand parameter by parameter what its role is, or you put them all together and then you reproduce nature. But I told my boss, okay, if it's to reproduce nature, myself, I prefer to go to nature. If it's to reproduce nature in a model, then, well, you may as well go into the nature. If it's so complex that you don't understand it. We had a bit of a rough time. So here we demonstrate that gravity-driven flow might be sufficient to create horizontal stretching in a context where the dominant context is crustal thickening. So next time you see a normal fault, you don't call upon crustal extension. It's not necessary. So then we played a bit more, and we said, okay, we're going to look at, with isostasy, there was no isostasy here, and we put isostasy, and we look at the same kinematic boundary condition with the plate going below another one, but then we put also thermal computation, rheology that is more complex, with radiogenic heat production in only the top part. And we managed to have a viscosity that goes from 10 to the 23 to 10 to the 19, between 400 and 700. Localize the gravity-driven flow in the zone of weak crust, whereas the top part becomes passive. I think that's very relevant to what happens to the Tibet plateau. No deformation on top, except on the sides, but still uplift by flow from underneath. But then I waited, because this is not what I wanted to show. I wanted to show collapse. No collapse. So we waited 75 million years, 100 million years, and the thing still kept going on. And then we're working with physics guy, he says, okay, but if you put water in a bottle, as long as the water is in the bottle, it's not going to flow. As long as there are strong vices on the side, there's no way this water is going to flow out. Took me 2 years to realize that water in the bottle is trapped. That's the physics, right? So in other words, this is not enough. The weakening of the orogenic root is not enough to promote collapse. It's good to explain the wedge plateau transition, but not collapse. So for collapse, well, you need to stop convergence, retreat, then you have collapse. and collapse, so I'm not going to go through that too much in details, but we identified different types of collapse. It was modeled also, the different types of collapse, and I'm going to finish with, not these ones, with this one. Okay, that's the final slide. So this thinking allowed to reappraise the orogenic cycle, with the first stage here represented here with crustal thickening on that side here and time. So the first stage is construction of orogenic wedge by burial exhumation, coupling, decoupling of crustal units from a downgoing slab. And at that stage, there might be a steady state. Erosion, if erosion is equal to the amount of material that comes by accretion, it might be steady state. And probably an example of that is New Zealand today. There's been a lot of convergence, but only a small mountain. And it's because there has been a lot of erosion. Same in Kamchatka. And people have found in sediments zircons that have probably made several times the circle, going from the top of the mountain, being eroded, going down to the fallen basin, going back to the orogen, and several times. So it means that the material is really going like this. But if not, then, this comes back to my first image, of flowed up tectonics, where buoyant units have been entrained at depth and then they decouple because of buoyancy and contribute to tectonic accretion. So then, if the crust is not eroded enough, then it continues to thicken and weakens at the bottom because of thermal relaxation, and the presence of this weak layer might control the wedge orogenic plateau transition. And this is the Saint-Nectaire tectonic, or flow of a weak lower crust. And in order to go from continental plateau or crustal wedge to collapse, then it's needed to change the boundary conditions, either stop convergence, that's the easiest, or retreat. And then if it's cold, then it's going to be a rift. If it's hot, it's going to be a metamorphic core complex. And as the crust thins, then it cools down because it will produce less heat product by radiogenic decay. And as it cools down, it will go from metamorphic core complex, basin and range, and eventually to a rift. And there we are, we have completed our orogenic cycle. And I think that's it. Yes, I finished with that. Do you find all the pieces that we had from the Western Alps, the Himalaya, Tibet, and the Aegean? They are all there. Do you have things that were not clear, or things, there, I do not agree with what you've said? You don't want to go into that? No? Okay. Are you too tired? You had enough today. Huh? There was a lot. Huh? But I think this will require for you time to digest. But I think one of the important things we want to show, and we did that also with Malika, contribution this morning, is to show how we go from different scales. We go from mineral scale, outcrop scale, regional scale, and then lithospheric scale. That's, I think, I'm always impressed that it works. You take a sample, you take a mineral, you date it, and it gives you a story. A story that you already had in mind for part of it, and then when gathering the data, you also get things that you didn't expect. And you're increasing your story, you're enriching it. This is really what I think is exciting in geology. Okay, I hope to see you this afternoon for the general presentation.
Yes.
Huh?
Please be here, or else no certificates.
No, but I think we reached to a totally different topic, but that is very relevant to society, I think.
So heavy, more light, more
Yeah. Or actually, I think it will be much heavier in terms of meaning for society.
Not so much conceptual.
No, not so much conceptual. It's easy.